All right, a sampler of Euler's number theory.
So as Dr. Hammett said, Jesse, Zach, and I are presenting on a sampler of Euler's number theory. I'm going to give you some history. Jesse's going to show us the proof, and Zach will take it away with the epilogue. So here we go, some history on Euler. Euler was born in Basel, Switzerland, and at the age of 1 year old, they actually moved to Rheims, a suburb very close, but he still commuted to school in Basel. During this time, he lived with his grandmother, and they weren't very wealthy, so he was sent to a very poor school district that actually did not teach mathematics at all. But lucky for him, his father obtained enough mathematical knowledge to get him through the concepts of elementary math, so he wouldn't fall behind since they couldn't afford one of the higher end schools. After his dad started teaching him mathematics, this actually sparked an interest for math in the brain of Euler, I'm right, okay.
Euler.
And so he began to read math textbooks, and he took private lessons on his own to continue to enhance these math skills. How his career began. Actually, he did not start in mathematics. At the age of 14, he attended the University of Basel, and he pursued a degree in ministry there. His dad was a minister, and he was very fond of him and looked up to him. And it was actually his dad's wish that he would follow in his footsteps and pursue ministry as well. So that is why he attended this university and did ministry to fulfill his dad's wishes and to pay him back for all that he had done for him in his life. So actually in 1723, he finished his master's degree in philosophy. This same year, he got out of school, began studying theology, and just discovered that he really didn't have the same passion and zeal for this subject that his father did. So he was really conflicted because he wanted to go back to school for mathematics, but he didn't want to disappoint his dad. Well, last week they talked about Johann Bernoulli. I said that right? Okay. He was a professor at the University of Basel, and he was good friends with the father of Euler. So he talked to Euler and was like, I think your son actually has the potential. I noticed it while he was at school, and I really think you should allow him to come back and pursue his dream in this. Luckily, his dad agreed, so he went back to school, and in 1726, he obtained his degree in mathematics from the same university. A year after his graduation, he published a paper about mathematics, and he actually got in a competition for it and received second place. So this was exciting for him, and he thought his career was going to take off, but a couple bumps in the road actually changed this. And in the same year, in April, he began boating to Russia, and he boated all the way to Russia and became a medical lieutenant for the Russian Navy. Fun fact. He did that for 4 years. So now number theory. The passion for number theory for Euler was actually sparked by Christian Goldbach. Goldbach loved number theory and had a great enthusiasm for it, but he actually didn't possess the intelligence to solve it himself and prove it. So he approached Euler. The only bad thing about this was Euler obtained the knowledge, but he didn't have the motivation that Goldbach did. So they just kind of pushed one another, and eventually they got Euler's curiosity to outweigh his lack of motivation, and he began to study number theory. How did Euler study number theory? Euler studied this theory by taking statements of Fermat, or making proofs of Fermat's statements. So Fermat was this great mathematician as well, but for the things in our book, he didn't actually prove what he had said. He would just make the statement, and then most mathematicians weren't smart enough to actually crack why it was true. So his statements just stayed more as theories rather than fact. So the first statement that Euler examined was the fact that some primes can be written as two perfect squares. As we go on this next slide, just remember that all primes are odd besides the number 2. So in this case, when we have all the primes other than 2, when we divide them by 4, we're going to have a remainder of either 1 or 3. So if we take the number 5 and we divide it by 4, we get 1 with the remainder of 1. You take 7, you divide it by 4, you get 1 with the remainder of 3, and the pattern just goes back and forth. So here we go. We can display both of these circumstances with the formulas P equals 4K plus 1 and P equals 4K plus 3. K represents the whole number, and then P represents the prime that we are dividing. Fermat came to the conclusion that those represented with the formula P equals 4K plus 1 can be written as the sum of two perfect squares, while those using P P equals 4K plus 3 cannot. A lot of mathematicians looked at this and they're like, that's not true, that's not possible. And they weren't able to prove it. So they just kind of thought, this is false. But actually in 1747, Euler came around and he was able to prove all of this true. So here we have some examples of those that fall under the category of P equals 4K plus 1. And you see the number 5, and its perfect squares are 1 and 4, 13, 9 and 4, 17, 16 and 1. And you see the pattern goes on and on for those numbers there. Amicable numbers. Has anyone ever heard of amicable numbers before? Dr. Hammett? Okay. So what is a pair of amicable numbers? I wanted to explain this really quick. So a pair of numbers, or amicable numbers, are a pair of numbers that follow the property which states the sum of all proper divisors of the first number equals exactly the second number, while vice versa. The proper divisors of the second number equals exactly the numbers of the first. So I know I kind of like said a lot of words there. So if you go down and look at the example, we have the numbers 220 and 284. And that's a list of what is divisible by. So 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. If you were to add all those up, you get the number 284. Now you take what 284 is divisible by, which is 1, 2, 4, 71, 142. You add those together and you get 220. So that's what makes them amicable numbers, because their divisors equal one another. So now, the past example that we just looked at was actually the only amicable pair known to man until Fermat discovered that 17,296 and 18,416 were amicable as well. I wouldn't want to have to prove that, because that'd be really hard to like map out what it was all divisible by. Take a long time. Descartes, I hope, was that right? Descartes, okay, found a third pair, but it was not until Euler the amicable numbers discovered their massive breakthrough. So over about 1,750 years, only 3 pairs of amicable numbers had been found. And then in a span of 4 years, Euler actually discovered 58 pairs of amicable numbers. So I think that kind of alludes to the intelligence that Euler possessed.
By the way, it's not that hard to check that.
It's not?
That those two numbers, no, because you just have to factor them into the product, into its prime factorization.
And then add them together.
And then you just, well, no, and then you can just build every divisor from the primes.
Okay.
You basically just say, well, I could take this many 2s and this many, up to this many 3s, and you can build all the divisors easily. So, I mean, Euler would have just instantly been like, I mean, of course, his brain is 18 times smarter than many of ours.
For real.
Also, but yeah, it's not that hard to actually check that those two are amicable. But what's stunning is that Fermat found those
in 4 years, when we found 3.
Well, Fermat found those two
yes.
numbers, but then Euler found 58 more. So.
Yeah, that's insane. So now Jesse is going to begin to explain the proof.
Okay. Well, hi guys. I'm in Faith, so it's going to make this a little bit complicated. Hopefully CJ can help by doing things on the board, I guess. I don't know. So first we need a little bit of background just so we can be able to do these problems. So if P is prime and it divides into like A times B times C times D, then P must divide evenly into at least one of the factors of A, B, C, and D. And then if P is prime and A is any whole number, then this whole big thing, A to the P minus 1 plus P minus 1 over 2 times 1 times A to the P minus 2, that's going to be a whole number because all of the fractions cancel out. And it looks really crazy there, but here's just, if you go to the next slide, a little example of it. Using A is 13 and P is 7. It follows that big long formula and just basically it all cancels out and you get a whole number. And then P must be prime or you don't get a whole number, because here it used 4 for P and 4 is obviously not prime. And it came out to a fraction, like a decimal 0.5. Next. Okay, so I need to move my little thing on here. Okay, so this theorem is that if P is prime and A is any whole number, then A plus 1 quantity to the P minus A to the P plus 1 is evenly divisible by P. So, so A plus 1 to the P equals that big long thing you see there, That's just how it works when you like multiply it all out.
That's just the binomial theorem. Jess.
Yes.
Yeah, right. Like that's what Newton did in a couple few presentations back. Yeah. So yeah.
Okay. So then you can substitute that in that the binomial theorem answer for a plus 1 to the p, and and then you subtract it by a to the p plus 1. And if I were on the board, I would just cross out the a to the p at the beginning and the end, and the ones at the end because they cancel out. And then you get your next step where all of those numbers have a factor of p in them. So in the next step, you just factor out the p. So then we know that a plus 1 to the p plus a to the p plus 1 is all divisible by p. No, CJ.
Oh, sorry.
No, that's okay. And the second step, or in the first step, like that first equal sign, the very first a to the p, and the a to p at the end. Okay, I don't know what's happening. But so then once those cancel out, everything has a factor of p. So you can factor out the p, so we know that p divides evenly by that whole thing. Okay. So our next theorem is that if p is prime and a to the p minus a is evenly divisible by p, then so is a plus 1 to the p minus a plus 1. So a condition of this is that a to the p minus a is evenly divisible by p. We test this by putting the whole a plus 1 to the p minus a plus 1 that we see in our bottom right corner, things that we know that we learned in our last step. We add a to the p minus p to that. Since we know that it's divisible by p, the whole thing should still be divisible by p. And when we do all of that, and we do the subtraction, again, you can cancel out the a to the p's. So then you just have like a plus 1 quantity to the p equals a plus 1 to the p minus a minus 1. And then you can just get this, that last step right there. So we know that that whole thing is also divisible by p. Okay.
Can you go back to the previous slide?
Yes. Second. Oops.
Okay, so the first thing, a plus 1 to the p minus the quantity a to the p plus 1, that's divisible by p because of what you just did earlier, right?
Mm-hmm.
A to the p minus a, that's going to be divisible by p because of what we did with Fermat's little theorem. Remember Fermat's little theorem? Like when we were doing cryptography and stuff?
Yeah, I think she's about to talk about that here in just a second.
Yeah,
right?
Yeah.
Okay. Ready for the next slide, Jesse?
Okay, so yeah, this is just a lot of little proofs that all like build on each other for random things. So this next theorem is if p is prime and a is any whole number, then p divides evenly into a to the p minus a. So Euler proved this using a like stair step theorem or something, where you like add one every time. We already proved that thing I've typed in there, that a plus 1 to the p minus a plus 1 is divisible by p. So we just kind of implement this here. So say you plug in 1 for a to the p minus 1 equals 1 minus 1 equals 0, and anything is divisible. You can divide anything by that. But then we can just keep adding 1. So like 1 plus 1 is 2, so 2 to the p minus 2, we know that's divisible by p. And then you just keep adding 1, and as I'm sure you can assume, it just goes on forever. So we know that for any whole number a, p divides into a to the p minus a. So this brings us to the little Fermat theorem, which states if p is prime and a is a whole number which does not have p as a factor, then a divides evenly into a to the p minus 1 minus a. So since we know that p divides evenly into a to the p minus a, we can just factor out an a, which gives us a to the p minus 1 minus 1. And since one of our conditions here is that a is not a factor of p, or doesn't have a factor, p is not a factor of a, it must be divisible by a to the p minus 1 minus 1 because of that thing we did at the very beginning, where if you multiply a times b times c times d and it is all divisible by p, then one of those has to be divisible by p. So if it's not divisible by a, which is a condition of the theorem, then it has to be divisible by the a to the p minus 1 minus 1. Okay, so Fermat had this conjecture where he said that all numbers 2 to the second to the n plus 1 are prime numbers. He had no way of proving this. He kind of just stated it, but Euler took a closer look at it. So as you can see on the left, if you do all of those, the first 4 are prime, but then when you get to the 5th one, 2 to the 32nd plus 1, it's this massive number, and it'd be really hard to prove. So the next few things we're going to do make this easier to understand and actually refutes this conjecture.
I have a question.
Yeah.
So Fermat's conjecture is that 2 to any power of 2 plus 1 is prime, right? Is that what that's saying? 2 to a power of 2 plus 1 is always prime.
Yes.
Is that right?
Yes.
And that's even true for like n equal to 0, isn't it? Because 2 to the 0 plus 1 is
1.
Or sorry, no. 2 to the 0 would be 1. 2 to the 1 plus 1 is 3, which is also prime. Yeah. Yeah. Okay. Got it. Sorry.
No, you're good. So for this first theorem, it's pretty easy, but we're going to just use like 3 of these to understand why 2 to the 32nd is not plus 1 is not prime. So this theorem states that if a is an even number and p is a prime that is not a factor of a, but it does divide evenly into a plus 1, then for some whole number k, p equals 2k plus 1. So that was a lot, but you need to know, so a is even, so a plus 1 is odd. And we assumed that p evenly divides into a plus 1, which is an odd number. So p must be odd. So p minus 1 would have to be even. So p minus 1 equals 2k, and k is just some number. Because p minus 1 is even, so it has to equal 2 times some number. And then if we just rearrange that, you get p equals 2k plus 1. Then for our next theorem, so suppose a is an even number and p is a prime that is not a factor of a, but such that p does not divide evenly into a squared plus 1. And for some whole number k, p equals 4k plus 1. So for this, we do something similar. And it's kind of what CJ talked about earlier, where any number divided by 4, any prime number divided by 4, you get 4k plus 1 or 4k plus 3. So now we have to figure out which one of those we want to use. So we'll go to the next slide. Just so we can rule it out, we look at 4k plus 3, and we decide that p cannot equal 4k plus 3 because of this. So we know that p is divisible by number 4 on the things we know. We know that a to the p minus 1 equals, when divided by p is a whole number. So if we just plug our things in, we have p equal to 4k plus 3, so we have that as our exponent. We subtract by 1, we get a to the 4k plus 2 minus 1. But we could just factor out a 2 in that exponent, and we have the same thing as in a squared plus 1. What am I doing? Oh, is also a divisor. So if we multiply those together, because if p is a factor of both, when you multiply them together, you should get something that still has a factor of p. But when you multiply those two big things together, it comes out simply to a to the 4k plus 2 plus 1. And then when we subtract them, a to the, this one is simply 4 plus 2 plus 1 minus a to the 4k plus 2 minus 1 equals 2, because when you, like a to the 6th, when you cancel it all out, I think there might be a typo in that a to the 4k. I think that should be to the 4k. When you cancel those two out, you get 1 plus 1, which is 2. And 2 is not divisible by p in this case. So we can roll out 4k plus 3 equals p. And you're left with, your only option is 4k plus 1 equals p is divisible by p. If that makes sense. So then we move to Theorem C. We're just adding powers to the exponent. We're adding to the exponent a, but suppose a is an even number and p is a prime that is not a factor of a, such that p does not divide evenly into a to the 4th plus 1. Then for any number k, p equals 8k to the 1st. So when you have any number and you divide by 8, you're going to have one of these remainders that you see in this picture. We can immediately eliminate 8k, 8k plus 2, 8k plus 4, 8k plus 6, because p is prime. It won't divide evenly because p will be odd, and those functions will be even. We can eliminate p equals 8k plus 3 because we proved that in Theorem B. And I'm not going to go into it, but if you work out p equals 8k plus 7, it's pretty much the same thing as Theorem B, and it won't work out. So 8k plus 1 is the one that works, but we're going to, on the next slide, talk about 8k plus 5 and show why that does not work. Okay. So it's basically the exact same reasoning as it was on the last couple slides for 4k plus 3. You plug your answer in for p, you subtract 1, and you get that whole thing, which should be divisible by p. And then you multiply it by something else that should be divisible by p, and you get a to the 4k plus 4 plus 1, which hypothetically should be divisible by p. And then you subtract it by a to the 8k plus 4 minus 1, which also should be divisible by p, and you get 2. And 2 is not divisible by p, so we know that that doesn't work. So a pattern kind of emerges from here. The only ones that work are the remainder of 1, the plus 1s. So if you see, like, for a to the 1st, it's 2k, a to the 2nd, it's 4k, so you just multiply the exponent by 2, and that's your coefficient with your k. So if we look back at what Fermat said about 2 to the 2nd to the n plus 1 being a prime, it gets pretty easy to disprove that 2 to the 32nd plus 1 is prime when you know this very last one, that if p divides evenly into a to the 32nd plus 1, p is in the form 64k plus 1. Your prime will be a multiple of 64 plus 1. Next slide. Okay, so it becomes really easy to test this because you can just start plugging things in for k and dividing your huge 2 to the 32nd by these big primes. So it didn't work for a lot of the numbers, but when k equals 10, you get 640 plus 1, which is 641. But when you divide 2 to the 32nd plus 1 by 641, you get this big number, 6,700,417. And that is also a prime. So we have found 2 primes that multiply together to get 2 to the 32nd plus 1, proving that it is not prime because 2 things multiply together to get it. So then actually they discovered that for n greater than or equal to 5, Fermat's conjecture is pretty much always false. So if it's like 2 to the 2nd to the 6th plus 1, that is not a prime either. Like none of the upper numbers are primes. So all those little theorems come together just to prove this one little thing, but yeah.
Now Zach.
All right, hello. So I'm also in quarantine, so bear with me on this one. But the epilogue talks about Carl Friedrich Gauss, who came after Euler. He was actually 6 the year Euler died. Gauss kind of ended up taking over as the lead mathematician in the world, or the most famous. We already discussed this, but just to reference back, he discovered the 17-sided regular polygon using Fermat's primes, which we discussed, but basically 2 to the 2 to the n plus 1 will not only give you a prime, but it will give you a regular polygon as well. So he plugged, if you can go to the next slide, CJ. He started with 0, which gave him 3, which was already commonly known as the equilateral triangle. Then he plugged 1 into that formula, which gave him 5, which is a pentagon. So then he tried to put 3 in there, and that gave him 17, which he then could decipher that was a regular polygon. If you want to go to the next one. But then he tried 4, which gave him 65,537 gone, which is, he could realize at that point that wouldn't apply to anything, since that's basically a circle at that point with that many sides. So then a little more background on Gauss. When he was in elementary school, there's a story of him with the rest of his class, and his teacher was getting a little frustrated with them. So she told the class to add up 1 through 100. So I guess she could get a little time and distract the kids. But a couple minutes later, little Gauss came up to the teacher and had the answer. And she checked it, and it was right. And she was very confused of how he could add up 1 plus 2 plus 3 all the way to 100. And his brain was so far ahead of everyone else's that he figured out a formula for it, which is basically the number. So what you want to add up to, so 100, then he would multiply it by 100 plus 1, and he'd divide that whole thing by 2, which gave him 5,050, excuse me. And if you had calculus, at least in our class, we discussed this because it has a lot to do with summation, and eventually leads into integrals, which he didn't discover, but he was a major part in that. He also went to college at 15 and earned his doctorate at 22, which is typically the average age is 33. So he was over 10 years ahead of everybody else in terms of math. He also proved the fundamental theory of algebra, which, if you want to go to the next slide. Oh, never mind. Go back one. Sorry. So the fundamental theory of algebra was started, but it was never fully explained. It was kind of implied. So he went back and actually fully proved that, which I'm not going to go through the entire proof because that's an entire lesson in itself, but just wanted to throw that out there.
Zach, do you know what the fundamental theorem of algebra says?
Is it it has to do with like negative b plus or minus the square root of 4ac, isn't it?
Well, that's what apply to quadratic, to second degree polynomials. But the fundamental theorem of algebra says that every polynomial factors completely if you include the imaginary numbers. That means that, so like if it's a 5th degree polynomial, it will have 5 roots. Some of them might be imaginary. If it's a 8th degree polynomial, it will have 8 roots. And so it will factor completely as linear factors. But yeah. Okay.
So this was a quote taken directly from the book, but I thought it was really nice to sum up Gauss's legacy. It says, Gauss was a man who published relatively little in his lifetime. The unpublished research found in his papers would have made the reputation of over a dozen mathematicians. Yet always mindful of the great expectations his work raised, he chose not to publish a result unless it was perfect and flawless as could be. Gauss did not write as much as Euler, but when he wrote, the mathematical world was advised to take notice. The fruits he left behind, from a regular 17 gone to the I'm not too sure how to pronounce that.
Disquisitionist.
Yes,
Disquisitionist.
to the mathematical fundamental theory of algebra, were as ripe as any that mathematics is likely to see. So I like the part where it says his work could have made the reputation of over a dozen mathematicians. That just shows how great he really was, and that relating this back to the actual presentation, Euler kind of laid the path for Gauss to run. The epilogue didn't have much to do with Euler at all, even using his proofs, but it kind of showed how he laid the path for Gauss to take off with mathematics.
So, oh, and then here are our sources, because we use some outside sources as well besides the book. But that is it from us three.
Wow, cool. Any questions for them? Questions?
He was in the Russian Navy.
He was from 1727 to 1730. He was a medical lieutenant there for 4 years.
Huh.
Find that on his biography online. Found that using the top source. I know. This is how I discovered it. So last night I was running through and I was like, I need something more interesting. I needed one more thing. So I was just like looking through. And if you like scroll deeper into his biography, it talks about him. I think the cooler thing is that he traveled by boat to get to Russia, but I'm pretty sure it was by himself. And he traveled for, I think it was 44 days, they said. And no, 54 days. And it's fascinating because he had a friend in Russia who wanted him to bring him tea and a couple other things. So he took stuff with him to his friend in Russia. But I didn't include that because it's not really necessary. I just included the medical part.
Cool.
So he went over there, gave the stuff to his friend, and then for the rest of the like, you joined the Navy.
He was in the Navy, and then there was something about a science. I can't think of the name of it. There was like a science school that he helped at, and he actually became like the head of something there. So he worked and did math over there as well. But he initially went over there to get away from Switzerland and went to his friend and served in the Navy. But he was still always tied to the Navy for several years after that. So after those 4 years, he wasn't done with the Navy. He was still a part of it. Just wasn't a medical lieutenant.
Did you get the feel as you studied the life of Euler and compared it to the life of Gauss, for instance, that there was a clear difference in character?
Yes, for sure. Because like something that I liked about Euler was he had a dream for himself, but he also wanted to honor his dad and live according to like what he wanted him to do. So he was actually a devout Christian. He just didn't have the passion to go into ministry, which we all know we can be Christians, but not want to be pastors someday. So I admire that about him, to give it a shot and actually get a degree in it and go pursue it and then decide it wasn't for him. So yeah.
Can I see this for a second?
Yes, you may.
Can I see the pen?
Yep.
Can you go back a few slides to where it talked about the sum,
Right here.
the story about the summation? So
Here we go.
Here's what Gauss did. Okay. He went like this. He said 1 plus 2 plus 3 plus etc. plus 99 plus 100. I don't know. I'm going to call that G for Gauss. Okay. And then what he did is he said, well, why don't I just write it like this down here? 100 plus 99 plus 98 plus etc. plus 2 plus 1. That's also G. Well, what happens if I add both of these things together? Okay, so down here, you get that this is equal to 2G, yeah? And what about all of these?
101.
Yeah, this, ooh, that's pretty. That's 101. What about this one?
101.
101,
101.
101. Hey, I think I see a pattern here. Okay, this is 101. This is 101.
How many 101s are there?
100.
Yeah,
No,
there's
50.
100. There's 100 101s. Therefore, we see that 2G is equal to 100 101s. Yeah, so what's G? 100 times 101 over
2.
2. So that's how he got 50, 50. Okay, he probably even did it faster than we just did it. But that's how we figured that out. And by the way, he realized, it doesn't matter. She could have asked me to go up to 1 million, and I still would have been able to pull it off, right? We got 1 million times 1,000,001 divided by 2, for instance. Yes. So that's a little 8-year-old Gauss. By the way, Gauss was a jerk even as a boy. Let me move this. Okay. But Gauss was a jerk even as a boy. Apparently, his mom at some point was pretty worried about him because he didn't have any friends. And he didn't care about that. He was almost like, sort of a kind of like a sociopath almost. and so she made an effort to try to get friends for him. And there's this story that one day, she invited some lady over, and this little boy was kind of playing with sticks outside, and Gauss was just standing there watching him. And she was listening, and she heard him say, "How many proofs of the Pythagorean theorem do you know?" He goes, "Huh?" And then he goes, "I know 7. And that's the sort of thing Gauss would do. And actually, he wasn't that much different when he was an adult. That's the sort of attitude that he generally espoused. But anyways, he was still brilliant, an amazing mind, but probably not the greatest example of character in the mathematical landscape. By the way, I think I wrote 100 when I meant to write 101 right here. Sorry about that. Yeah.
No, that's great. Oh, no, you're no.
It was 101. Yeah. Sorry. Other questions? Cool. I think there's one more presentation to do. It will probably happen. We'll probably just have it on Friday, although that's a little bit questionable because I know that the finals are supposed to start on Friday. Okay. Do they start Friday or no?
They start Thursday.
They start on Thursday. Friday's the replay.
Yeah. Oh, what is going on? I'm getting lost by the
I know,
schedule.
it's confusing.
So Friday is a normal day, right? So there's one more. And again, I sent out kind of basically a summary, or what I think is a really good article with lots of sources if you want to look at them on the Cantor set. Okay, so I'll be in touch with those of you that have not presented yet. And then next Friday, there are those 3 capstone seminars. Like I said, I don't think they last for an entire hour, even though they're slated for an hour. I'm going to make sure that those get recorded, so you can at least watch those. And as far as the second part of the flatland thing, that will just be due. Look, we're just hanging on by the seat of our pants at this point, right? That will just be due at some point, probably at the beginning of finals week. Okay, so you just kind of plan on that. We will have probably some time to even take a peek at this little movie that will take about half of a class period, and we'll talk through some of the differences. If it was accurate in accordance with the actual book itself. I think you'll know pretty quickly what the answer to that question is. Okay, so it'll be an interesting discussion. All right, sir. I'm going to attend, and I'll kind of watch the participant list, and I'll just mark it down. Yeah, and I'll sort of double check with you, but I'll mark down who's actually there. I'll be sitting there watching, and I'll be kind of tracking who's there and who's not there. Yeah, Anna.
Are you able to tell us what we should be studying for the final?
Yeah, so I would try to really study and hone in, especially on like the sort of number, like we had that big sort of number theory section. I think that's a really good thing for you to hone in on, sure. Okay, just trying to understand, not necessarily like, not that I'm going to ask you to prove like Fermat's last theorem, or of course not Fermat's last theorem, Fermat's little theorem, which we did prove, by the way, visually. But at least know what it says, how to apply it, for instance. And we did several examples in class of like the RSA implementation, right? I think RSA is a good thing to kind of focus in on, try to understand or recall what it is that we were doing there, right? We did a lot of like build up there of like basic number theory and modular arithmetic. But I think those two things, especially Fermat's little theorem, kind of RSA, those are two things I want you to be well familiar with. Other questions? Man, there is a giant collection of people in quarantine right now, which is sort of unfortunate, but yeah. All right.
You're welcome for that one.
Well, thank you guys. Thank you. Have a good weekend.
Have a good quarantine. Is there anything else you need from us, Brent?
I don't think so.
Okay.
I'm going to download a copy of this. I can just do it right here.
Okay.
No problem.
Perfect.
You say that you'll be like issuing the final like Wednesday of next week or something.
Yeah. I'll do that. Yep.
How long typically does it take until we know what we scored on